All right, so we started LU decomposition last time. And what LU decomposition is, it's really just the adaptation in the strategy how we do solving of our systems for the cases where I'm solving multiple systems that have the same matrix A, so I'm in business of solving AX is equal to B. And in that business, sometimes I will actually solve multiple systems with same A, but different right-hand sides B. Why is that? What are some examples that I mentioned? What are the cases where I might actually have the same A physically, with some physical problem? What is typically in A? What I call hardware of my physical problem. Okay? So basically, if I'm setting up flow through a flow network of sorts, okay, whatever that flow network might be, the hardware I would call the size of the pipes that I'm using. And those size of the pipes will actually ultimately determine coefficients in A. And it's really fluxes that I'm putting into the system, which is my boundary conditions, stuff that is entering in and out the entire system, that is typically on the right-hand side B. If you remember that problem with the temperature, where I had a rod and I was calculating temperatures along the rod, and I had some boundary conditions in terms of the temperatures on either side of the rod, right? Remember those walls? Those temperatures that I'm putting in, like it was 40 and 200, I believe, Celsius degrees, okay? Those numbers would end up in B. When I'm setting up my linear systems, they would end up in B. But they're really the boundary conditions that I'm controlling. I'm not changing the rod itself. As far as material that rod is made of, and the surrounding air temperature, those were things that were actually built into A. And if I keep those constant, right, and all I'm changing is those other temperatures at the ends, then all I'm changing is B, and my A remained the same if I'm thinking about the system AX, or we had T, AT is equal to B. Does that make sense? So there is a lot of, point is that there's a lot of cases where that might be the case. The second problem, or the second type of the problem, is finding inverse of matrix A, and I went through sort of like analysis of how basically finding inverse of a matrix is equivalent to finding columns of that matrix. So essentially, with my system A being the same, AX is equal to identity, columns of identity matrix, and I can split that problem up into finding N being the number of columns, linear systems that all have the same A, it's just that side B that is changed. Okay? So we have, as a recap, we have situations, a lot of situations where I might be solving system AX is equal to B, where only B is changing and A remains fixed. And in that case, we're using this strategy called LU decomposition. Okay. So let's just recap what LU decomposition is about. So just to recap, LU decomposition, it's a strategy for reducing number of computations when solving AX is equal to B, and I'm going to say here BK, K is 1 through who knows. So basically, all I am changing here is the right-hand side. Okay. A remains the same. So we know that if I was to use Gaussian elimination on this, I would effectively have two steps in Gaussian elimination, we would first have forward elimination, and then we would have backward substitution, or back substitution rather, backward. Well, same thing, backward. Okay. So those are the steps that we do when we actually solve the system by Gaussian elimination. And I explained briefly last time how if I was actually about to count number of additions and multiplications and divisions and subtractions that you have in a system that is n by n. So if I have n by n system, okay, then this forward elimination would take O of n cubed, which is a lot. And we kind of tried it ourselves and see how it can take a long time when I have a larger matrix. And this is O of n squared, where this means order of. So whether it's 2n squared or 3n squared plus 5, it doesn't matter. It's sort of like the order of magnitude is similar to n squared. And more importantly, if my number of unknowns changes from n to 10n, okay, this goes up 1,000 times, not 10 times, but 1,000 times, okay? If my size of the number of unknowns that I'm looking for, if it goes by 10 times, this will go 1,000 times, and this will go 100 times. So that's a big deal, okay? Now in LU decomposition, especially if I have to, let's say that I have to solve this problem 5 times, okay? I would have 5 times, let's just call it n cubed plus n squared, if solving 5 times, right? So this is time required, or the order of complexity. Whereas what LU composition says, hey, for these problems that you have AX is equal to some size B that changes, like first time you go about, you solve this, and actually there's something you can record. In this process, you can record 2 matrices, one lower triangular, one upper triangular, L and U, such that A is LU. Okay? If you do that, then this you do only once. So in LU decomposition, you do this step forward elimination, do only once, save L and U, okay, such that A is equal to LU. And then every time you change this right-hand side, you repeat. So every time new right-hand side comes along, we will do 2 steps. One step will be solving LD is equal to B, and another step will be UX is equal to this D that we just found. And since this is lower triangular, this is upper triangular, it's cheaper to do this. It's actually O of n squared, O of n squared, both these steps, and this is my O of n cubed part that is expensive. So if I'm doing this once, then all I have is n cubed plus, and then I'll do this 5 times for 5 different systems, right? 5 times 2n squared, right? If solving 5 different times for 5 different B's, or right-hand side. So this, in terms of number of operations and therefore the time that it takes, this is way less than this. Yes?
Can you go over what you mean the last 3 lines LD?
So we will actually, if I solve LD is equal to B, right, and UX is equal to D, I have effectively solved AX is equal to B. Let me show it to you. So I'll open a new page, okay? So basically solving this, if my A is equal to LU, okay, solving this will give me X that says that AX is equal to B. Let me go through that. Let me just find a new page. Okay. So basically, if I'm solving AX is equal to B, let's say, okay? So if my A is LU, then that's same as LUX is equal to B, correct? So in order to find X, okay, I'm first finding D. Step 1, find D such that LD is equal to B. So I don't have it to begin with, but I have L and I have B, right? If I did my forward elimination step and I recorded L and U, so I have A is equal to LU. Then I can find D, it's an unknown, and LD is equal to B. Do you agree with me? Okay, so I have B, I have D, I have L, I can find D such that LD is equal to B. Yes? So once I have that B, then I use that B, and in step 2, I will find X such that, UX is equal to D, where this D that I found is the same. Yes? And if UX is equal to D, LD is equal to B, well, then A, since A is LU, AX is equal to B. So I found the solution to my original system. Am I speaking Croatian? So if UX, first I find D, I don't have it, right? But I have L. Okay. So if I find the LD, this is just solving this lower triangular system, and we will go through the problem. So if LD is equal to B, and my D, I find X such that UX is D, then LUX is B, but LU is A, so AX is B. So I found the X that I needed to find. Okay? Now, last time around, where did we end up? We have completed LU decomposition. Okay. So last time, so continue example from last time. And what I had there is I was going through forward elimination. And one thing that was important is to do things in specific order. So when I'm replacing my row, I was replacing, for instance, I had initially 3 minus 1. I'm just going to So then I was actually very careful to replace 2 to minus A21 over A11 times first row. And this I recorded as L21, which is equal to minus 2. And then we did the elimination. And the second one we replaced by 3 minus A31 over A111. And I'm just going to record this on a side and say, oh, my L31 is equal to 3 over minus 3, so it's minus 1. And that gave me a matrix, and I'm just going to write down what we got because we went through the computation last time already. And again, I'm going to be careful about applying the same rule, so I'm going to replace the third row with 3 minus, this is now A32 over A22. And I'm going to put a tilde because it's different from my original matrix. So I can't just go to my original A because this is now these positions as I see them right here after some modification. Okay? So this is my new coefficient. So this little tilde means whatever, like I'm changing the matrix as I go, so take those change elements, don't go to the original matrix. So then this here is L32 is equal to 1, minus 2 over minus 2. And when I do the replacement, this will become, I'm just going to write it here, 0, and this will become minus 2. I don't want to read. You can rewrite. So at the end of this, once I have zeros where I wanted zeros to create upper triangular matrix, then that's my, and I'm going to do everything on this same slide so I don't have to go look it up. So basically my ultimate upper triangular matrix is minus 3, 2, minus 1, 0, minus 2, 5, and 0, 0, minus 2. And my L is, it's going to have 1 on diagonal, zeros in my upper triangle, and it's a lower triangular matrix. Its L21 will be minus 2. It's this number. Its L31 will be minus 1, and its L32 will be 1. And A is LU. Now let's see that that's really the case. I'm just going to quickly fire up MATLAB and do the matrix. I could do it by hand, but I'm going to trust my software on this matrix multiplication better. So basically, I'm just going to prove it to you that A is indeed equal to LU. So my L is 1, 0, 0, minus 2, 1, 0, and minus 1, 1, 1. And my U got reduced to minus 3, 2, minus 1, 0, minus 2, 5, 0, 0, minus 2. Let's do L times U. It's -3, 2, -1, 6, -6, 7, and 3, -4, 4. That's what I have. That's what I started from. Is finding L and U such that A is equal to L times U unique? Can I do it only in one way? Probably not. And that's why we set this diagonal to be ones, in order to lock it down to one choice. Okay? But there is multiple ways, and that's a little frustrating, because if you actually fire, there's a function called LU that will probably do slightly something different. Okay? But as long as L times U is equal to A, you can work with that. So if you switch the rows, you will actually probably switch the rows in ultimate A, but also your L and U will not necessarily be diagonal then, or lower and upper time. But these coefficients can kind of change. For one, if you see -3 times 1, okay, because of the zeros, -3 times 1 ultimately ends up in this location here. Well, you can multiply -3 here by 2 and divide the one that you have in L by 2, and you're going to get the same. So that's just there you have a number of options for coefficients to be. But that's why we are setting this diagonal to 1. So my point is that if your L, essentially, if your U had -3 over 2 here, and your L had 2 times 1 here, you'd get the same result essentially, but you would modify other coefficients to fit that slightly. But that gives you various choices of L and U, which is why we're fixing this position here to be 1. Okay. So now we have L and U. What are our next steps? Let's say that I'm actually set on solving a problem, okay? So I did this first step where I separate, I have A is equal to L and U, L times U. Let's say that we are trying to find the inverse of this matrix, okay? So assume we are trying to find the inverse. Okay? Inverse, A inverse, I'm going to refer to it as A to the -1, is such a matrix that A inverse is identity matrix. So this is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Basically, if I assume that this matrix here is basically, I'm just going to call columns of A inverse as x1, x2, and x3. So I have 3 columns. Then this problem, or finding this inverse, is same as finding A x1 is equal to 1, 0, 0. So basically, A times this first column is this first column here. A x1 is this. Okay. If you actually do the matrix multiplication, that's what it comes down to. And A x2, so A times this second column is this. And A times this third column is this. So I need to solve 3 systems that have same A, okay, but different right-hand side. In one case it's 1, 0, 0, in another 0, 1, 0, and in third 0, 0, 1. I already have L and U. I have LU such that A is equal to LU. Let's say that I'm solving this thing first. What am I supposed to do now? What is the first thing that I'm solving now? It's back in your notes from 10 minutes ago. Flip through your notes. I'm going to call this B1. What am I solving first? In order to solve this problem, I have to use L and U. How? Go to your notes. Find D. So step 1, find D such that what? L times D is B, this B1, right? Which is 1, 0, 0. What is my L? So my step 1 is L, and I'm going to write it in augmented form just because it's simpler. So it's 1, 0, 0, minus 2, 1, 0, minus 1, 1, and 1, 0, 0. Yes? So I can just, what's the first thing I can solve for? What is x1? Great. So x1 is equal to 1. That's from here. Then from here I get what? Minus 2 times 1 plus x2 is equal to 0. What is x2? 2. It's that simple. These are actually, when I have a lot of zeros, it's going fast. Here I have minus x1, which is minus 1, plus 2, plus x3 is equal to 0. What is x3? Minus 1, right? So my column that I'm calling x1 is 1, 2, minus 1. That is the first column of my inverse matrix. Okay? Oh, not yet. This was D. Nobody's saying anything. Not there yet. So that's my D. Step 2. Now that I have D, now I find X, and I can call it X1, as in just the first one that I'm looking for, such that UX is equal to this D, which is 1, 2, minus 1. So now I will have back substitution. Okay. So now my next step is u, what is my u? Can somebody read it out for me? And then my d was what?
0, 0, 8. E was
1, 2, negative 1. Okay. So now this is back substitution, so now I'm looking for x that solves this problem, so I start from x3 because in back substitution with upper triangular matrix, that's the first thing that I do. So my x3 is minus 1 over minus 2, right? Which is 1/2, 0.5, however you want to look at it. Then I put that in here. Minus 2x2 plus 5 over 2 is 2. 2 is 4 over 2. Minus 5 over 2 is minus 1 over 2, right? Divided by minus 2, what is my x2? Somebody check on me. And then I put both of these into my first equation. So I'm going to have minus 3x1 plus 2 times 1 over 4 and minus 1 times 1 over 2 is equal to 1. This is 1/2 minus 1/2. This actually cancels out. And my x1 is minus 1 over 3. So this is my first column of A inverse. And just a recap, why is this x1 that we call, why is it actually solving our original question, ax1 is that b1? It's because based on this back substitution, we found x such that ux1 is equal to that d that I found, right? And I know that LD, we found D such that LD is that B1, right? So this means that L times UX1 is equal to B. And since LU is equal to A, that means that AX1 is B1. So we did indeed solve our problem that we started with. And even here, as I'm solving by hand, comparatively speaking, these two, this is an upper triangular, this is a lower triangular, they're relatively easy to solve. L also has ones on diagonal, so kind of it goes quickly. It just takes a little bit of. So now, what would I do to find my second and third column of A inverse? Repeat. Okay, so this is the dull part. So repeat for AX2 is equal to 0, 1, 0. Yes.
Is there a faster way to solve this?
By hand? No.
Yeah.
This is why This is the whole motivation why you want to program. Okay, ultimately you want to. There would be some. We separated it into this. There's multiple ways you could go about it. So in your linear algebra, you probably just put.
Made any new matrix on the other side and then made that look like it.
But
Did
what?
math that, does that not work?
Well, it does. The reason why this is broken apart this way is that that's what ultimately software behind that is speeding things up is doing, and I want you to understand that part. That's all. Okay. But by hand, you would probably put both A and all of the 1 0 0 0 1 0 0 0 1, and then you would do it all, right? But I want you to understand that with software, the way you would program this is you would go and record, you would do forward elimination, you would go and record L and U, and then work with that if you want to reduce the number of computations that is happening. Okay? So by hand, yes, I agree, you would probably compile them both together and just drive all of them at the same time.
That's what I'm doing.
And any larger, especially any larger problems, like especially when you have a problem thousands by thousands and so forth. Okay, that's all. So you have to record them and you, and then repeat with those. Otherwise, you're not cutting down the number of operations. Okay. Well, and to some extent you are. It's just harder to see, and I want you to break these things down just to see it. You are still actually doing things, working separately. You just kind of don't see that if we pile it all together. And I'm just gonna actually, so again, I'm gonna help myself with software here. So basically, what we would do is we would again, in step 1, we would basically solve LD is equal to 0, 1, 0, okay? And step 2, UX2 is this D, after I find D. So how about I help myself? D is L divided by 0, 1, 0. Okay? And then my X, I'm going to call it X2. My second column would be U divided by D. So it says that this would give me dot, 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 in the same procedure as we just did. My X2 is 1/3, 3/4, and 1/2. You agree with me? Yes.
Shouldn't D be 0, 1, 0 divided by L?
No. We always put A/B, right? So if you have LD is equal to something, then it's L divided by that. That's just the way this backslash operator works, right? And I'm just gonna quickly repeat this for 0, 0, 1. And then my X3 is this. So what is this? Minus 2/3, minus 5/4, and minus 1/2. And similarly, also X3 dot 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 is minus 2/3, minus 5/4, and minus 1/2. So one last check. If I actually have a matrix that has, so my X1 was what? Minus 1/3.
1 over 4 and 1 over 2. Oops. What did I do wrong? Ah, one bracket missing. Okay, so I have my x1, x2, x3. What is my inverse of A? My x1 was minus 1 over 3, 1 over 4, 1.5. Do I see it here? Yes, I do. My x2 is this column. Do I see it here? Yes, I do. My x3 is this. Do I see it here? Yes. So I verified that we actually did, well, some of this was done by hand. Most of it was not. Okay. But I actually verified the steps that we did it right. So we found the inverse.